Hey, AP Chemistry class, this is Miss Gray, and we're still in Unit 3, Special Reactions. Today we're going to focus on acid-base reactions in particular. These ones can be pretty exciting. First, let's define what we mean by acid. When we talk about an acid, essentially we're talking about a substance that will ionize in aqueous solutions when we dissolve it in water to form hydrogen ions. So either it produces its own or it liberates them from the water. But the overall accomplishment here is that we've increased the hydrogen ion concentration of the solution as a whole. We also would call this ion a proton because remember, hydrogen's made of an electron and a proton, so if we take the electron away, all we have left is a proton. You'll also hear this called the hydronium ion, although often a hydronium ion is written like this, where we just take that proton and attach it to water. But it's the same idea that there's an extra hydrogen ion charged particle around. Monoprotic acids are the ones that release only one hydrogen ion, like hydrochloric acid. You know what, let's ionize that real quick. Hydrochloric acid breaks apart into these ions, hydrogen ions and chloride ions. So for every one molecule of HCl, you get one ion of protons and one ion of chlorides. Diprotic acids release two. So the first step would be to dissociate the first hydrogen from, say, H2SO4, and you're left with another hydrogen still attached to that particle. So this is what makes sulfuric acid in particular a strong base, because not only do we get this dissociation, but the next step is automatic as well, where the second proton pulls away and you're left with a sulfate ion. As you can imagine, things with a 3- charge are going to be triprotics. Never heard of anything higher than that, but you know, there could be such a thing. Triprotic acids would have 3 steps to ionize, but it would be very similar to what the diprotic acid did. Each of these steps has its own equilibrium, so you'll have to know which ones are strong acids and which ones are strong bases. So let's talk about bases. A base is a substance that will either accept that hydrogen ion or react with a hydrogen ion. Another definition of base is that they will produce the hydroxide ion when they dissolve in water, either by stealing away that proton, right? We talked about how it will accept these. Well, if it accepts it from water, then we've left this behind, right? So that produces the hydroxide ions because it steals the hydrogen away from the water, or they might just dissociate and break into hydrogen ions themselves. So let's see an example of those. Here's an example of something that breaks down and releases its own hydroxide ions. Sodium hydroxide, it's one of your strong bases. Calcium hydroxide will release 2 hydroxide ions. And then here's one that steals that hydrogen from water. See, ammonia is going to take a proton from water and add it to its own molecule, and it actually adds stability. See, ammonia has this Lewis structure. If we were to draw what it looks like, then this is what that molecule looks like. And these electrons here are what that proton is attracted to, right? A positive charge and a negative charge are attracted, so it adds stability to the entire structure to exist as a charged particle. That's why ammonium ions are fairly stable and they don't dissolve, they do always dissolve. They never are precipitates because they're so stable in water. But then when we take this proton here, this guy, when we take it from a water molecule, then what's left? Here's our water, HOH. If we take this proton away, then we're left with a hydroxide ion. So that's why ammonia is basic, not because it has a hydroxide to release, but because it accepts that proton from the water and leaves the hydroxide behind. So bases are going to be increasing your concentration of hydroxide ions, whether it comes from that particle itself or whether it's coming from the water. So pay attention Let's see that again. Pay attention to stoichiometry. How many hydroxides are being released and how many protons can be released from those molecules. Acid-base reactions, of course, are where we add an acid to a base or a base to an acid. We call these neutralization reactions because it's going to lower the concentration of either the protons in solution or the hydroxides in solution, and typically both, and then produce water and a salt. So here's an example, very simple acid-base reaction, hydrochloric acid and sodium hydroxide. And what we make is a salt you're very familiar with, sodium chloride, because this is a double replacement reaction, right? We take our cations, let them trade places with one another, and then we get water and a salt. This is exactly what you get every single reaction. You get a water and a salt every time an acid reacts with a base, unless it's a Lewis acid. We'll talk about those in a little bit. So a salt is any ionic compound whose cation comes from a base and anion comes from an acid. So there's a lot of different types of salt, like magnesium sulfate would come from sulfuric acid and magnesium hydroxide. Magnesium sulfate is called Epsom salt, and you can soak your tired and sore muscles in that, apparently. I've never tried it. I've just heard you could. We're going to do a titration demo in class, so be ready to summarize what your observations were that day, and let's look at strong acids and strong bases. When we were going over how to name things, we talked about which ones are strong, and you need to memorize these. You just do. So if you don't already have flashcards with the formulas and names of these things, make them today. Push pause on your podcast and go get your index cards and get your flashcards done, because you need to know that these ones are the strong acids and which ones are your strong bases. Remember, they're based on the solubility rules. All right, weak acids and weak bases are weak electrolytes, and so they don't break apart completely in water, and they're not going to form as large of a concentration as something that does completely dissociate. So here's acetic acid, and then we're going to pull this proton off so that now we have a negative particle and a positive particle. And we're also going to have in our solution some of these that didn't break apart. So when we take vinegar, which is acetic acid, and we put it in water, then this is what we get. Some particles break up and some particles stay together. So these are the molecules and these are the ions. Which ones are the ones that will conduct electricity? Right, the ions. Only the ions that break apart are then free to move about, and moving charges is how we get electricity. So those are weak electrolytes. Oh, look, here's another one. Let's get rid of the writing so we can see it. HF is hydrofluoric acid. So again, we can pull off that hydrogen ion, and we'd be left with a fluoride ion, and we're going to have some particles in that solution that are still molecular, that did not break apart, because fluorine is going to hold on to that electron that it shares with the hydrogen, and it's going to hold that covalent bond together pretty tightly. Right? Here's this particle. Yep. And H2CO3, every time you see this as a product, I need you to do something special with it. It will decompose when it's a product. When it's a reactant, then you need to understand that it's going to be 2 hydrogen ions and 1 carbonate ion. But when it's a product of a reaction, then you're going to write it as water and carbon dioxide. Just like in your soda pop, this is what it turns into. Carbonic acid is added to your soda so that it will be fizzy, so that it will turn into bubbles of carbon dioxide. So when carbonic acid is formed as a product, you need to write it like this and never like this, because it just won't exist that way. It decomposes. All right, let's look at some weak bases. Beryllium hydroxide is a weak base because that's not soluble in water, right? Beryllium hydroxide is insoluble. So truth be told, by insoluble we mean weakly soluble. Only a little bit of it breaks apart into these ions, but not very much. Most of it is going to be in molecular form still, BeOH2. So we'll have all three types of particles. Oops, we need an E there. All three types of particles in our solution. We'll have some of these and some of these, but most of what we will have are the molecular particles, not the ions. Magnesium hydroxide is also weakly soluble, more so than beryllium hydroxide. It typically exists as a suspension, and you may have seen this in your medicine cabinet. It's called milk of magnesia, MOM, because magnesium hydroxide can help to settle a stomach that's too acidic. And then NH3, we just talked about how that steals the hydrogen ion from the water and leaves hydroxides behind. Let's look at naming bases. Basically, a base keeps its own name. So you just name the ions that make it and you're done. Beryllium and hydroxide make beryllium hydroxide. This goofy one, ammonia, is one that's covalent, but we won't call it nitrogen trihydride. Please memorize this one. If you haven't already, this is ammonia, and that will help you a lot because then we're going to be using this type of thing to make amine groups and amino acids and all kinds of other things. And all of those names derive from ammonia. All right, how about naming acids? This gets a little trickier, but let's look at each type of acid. If you have a monatomic anion, then you start with hydro and you end with ic, right? So hydrochloric, hydrofluoric, hydroiodic, hydrobromic. If all you have is a binary acid, like this one right here, then hydro is the beginning, ic is the ending. And then work the middle so that pronunciation seems right. Okay, let's look at polyatomic ions, like, I don't know, carbonate. We had that one right here. So if it ends with 8, then all we do to the ending is put an ic on the end, nothing on the beginning. Carbonate becomes carbonic acid. And of course, all of these have the word acid at the end. If our polyatomic ion ends with ite, let's use chlorite for an example. Chlorite has this formula, ClO2 with a -1 charge. So that tells us we need 1 hydrogen to make chlorous acid, HClO2. So if the ending is an ite, then we change it to us. And if the ending is an ate, we change it to ic. You know why? Because I ate something icky. Ates become ics. Let's look at acid-base theories then. Who came up with this in the first place? It's been a long time that we've known about acids and bases, but the chemical processes are, well, complicated. So we have 3 different definitions: the Arrhenius acid-base definition, the Bronsted Lowry acid-base, and these are the most common ones. And then we also have Lewis acids and bases, because what we've seen is that in the lab, the theories that we had before needed to be modified, where, well, this describes some acidic behavior, but not all. And so these are modifications or additions to what we already understood. The Arrhenius model was proposed in 1887 by a Swedish chemist, Svante Arrhenius, and he basically said that acids are compounds that have hydrogens in them, and they break apart to make protons in solution. And bases are compounds that have hydroxide, and they'll break apart to yield a hydroxide ion in solution. So you can see one of these problems here is that not all acids have their own hydrogen ions. Sometimes they just liberate them from the water, and not all bases have their own hydroxides. So this was a good start though, right? In the Arrhenius base, then you'd have an alkali metal that's the strongest because they always dissolve in water. But that neglects other strong bases like strontium, barium, and not magnesium. What was it? Barium, strontium, calcium. Gotta say them in order. I just don't know them. Crazy, isn't it? So here's an example of an Arrhenius acid. The reason why vinegar is an acid is that it will leave off that hydrogen ion. So the carbon has a lower electronegativity than the oxygen. Only the hydrogen that's attached to the oxygen will break off. Let's show this molecular structure so you can see what we mean. You see, in acetic acid, there's hydrogens attached to the carbon. And then there's other hydrogens that are attached to the oxygen. So what we're saying here is that these hydrogens are not going to easily pull away, whereas this one will. Why? Because oxygen is highly electronegative. So there's these two oxygens here that tug on all the electrons, and hydrogen doesn't get to share. If you go to a friend's house and he doesn't share his Legos with you, you'll probably go find somewhere else to play, right? Because he doesn't share very nicely. Oxygen does not share electrons very nicely. So the hydrogen leaves and goes to play somewhere else. But he has to leave the electrons behind because oxygen took them. What a bully. So let's look at Bronsted Lowry's definition. How do I clear? The Bronsted Lowry definition gave us the ability to describe acidic behaviors of other types of compounds that didn't already have a hydrogen in them. He described acids as hydrogen ion donors and bases as hydrogen ion acceptors. An example is hydrochloric acid. So hydrochloric acid donates a hydrogen and then it's accepted by the water. So in every reaction, you would have not just an acid and a base, but you would also then describe a conjugate acid, the thing that accepted that hydrogen now can donate it back over here. And then the conjugate base is now a hydrogen ion acceptor, right? Because it got rid of its hydrogen ion, it could take it back, and that makes it now a base, because technically it is able to accept that ion. That particular one won't accept the ion. You know why? That's a strong acid. But ammonia is a good example because it is going to accept the hydrogen ion from water. So here's our base, and then here's our acid. Because the water is giving a hydrogen ion away, it's classified as an acid by the Bronsted Lowry definition. So we get a conjugate acid here because now this ammonium, conjugate acid, now this ammonium could potentially give away that proton, right? And then this is your conjugate base because hydroxide can now accept that hydrogen ion. So we always have conjugate acids and bases, and you'll get lots of practice at identifying these. Oh, look, I already wrote it. I didn't have to write all that stuff again. Oh, well, that was good for us. Whoops, sorry, wrong button. Okay, yep, we did this. Here's where life gets strange. Under this definition, we can have a substance that acts as both an acid and a base. Water is the most famous one. Water will both accept a hydrogen ion to make the hydronium ion, and that should have a plus charge right there. And other times it will donate a hydrogen to form the hydroxide. So if this is just liberated out there into the water and these are equal, then you're going to have a neutral substance still, just pH of 7 for water. But if this gets used up by something else, then you're going to have hydroxides outweighing the hydrogen ions. right? So if ammonia comes along and takes some of these, then the hydroxides now are more than the hydrogen ions, and your pH rises. On the other hand, if we had something that could use up these hydroxides, suppose I put something insoluble in there, like, I don't know, aluminum, say. Aluminum hydroxide is not soluble in water. So aluminum could take these out of solution. They would precipitate out, and then our pH would, decrease. pH would decrease because we have now more hydrogen ions in solution than hydroxide ions. So if we have a substance like this, then we call it amphoteric because it can be either an acid or a base. Metals and metal oxides often act this way, like the aluminum. It could act as an acid or as a base, depending on the conditions. Amino acids have one end that's acidic and one end that's got an ammonia on it. So that's why they're called amino acids. And proteins and ammonia can do both. So let's look at Lewis acids. This is our last theory about acids and bases. This Gilbert Lewis is the Lewis dot guy, right? So this has got to be all about electrons and pairs of electrons. You see, a hydrogen ion has a pair of electrons that it could accept, right? Because it doesn't have any of its own. Let's see this. H plus. All it is a proton. So if I put 2 electrons with it, then I would get an H minus. And then that would be just as stable as the H plus. A Lewis base could donate a pair of electrons, and let's look at what water does with this. So suppose that we have the hydrogen ion. It has room to accept an electron, and then the hydroxide has an extra electron to donate. So let's look at this definition of acids and bases. Which one is the acid here? The acid can accept the pair of electrons. So this particle is acidic, just like in Bronsted Lowry. And the bases can donate a pair of electrons, and so here's where we have extra electrons to donate. This piece then is considered our base. And when acids and base react, they form water and a salt if other ions are present. So really we haven't changed the definition, but we've now been able to extend the definition to include other substances like boron trifluoride. This one's a weirdo because boron has these 3 valence electrons, and then if it joins up with fluorine, then it's only going to have 6 electrons around it and not 8. Boron's a weirdo because it can tolerate being hypovalent, having not enough electrons to complete the octet because it's such a small particle. This is actually a stable configuration. But look right here, if we were going to complete the octet, we would add 2 electrons there, right? To complete the octet. So what do you think boron trifluoride would be considered? If it has a place for electrons to go, then it's going to accept electrons. That makes it a very common Lewis acid. So if you see in a reaction, that boron trifluoride is involved, then you're looking at a Lewis acid-base reaction. And what we do then is combine our acid with our base to form one molecule, like a combination reaction. So I'm going to show you how to do some of those in our examples.